Hello, Carol again, working out a collisions problem from the momentum chapter of Physics 110. Here we have two-dimensional collision. So we're imagining a car crash here where we have car A with a mass of 950 kilograms coming in at 12 meters per second, crashing into car B, which is stopped at the moment. So this is all before the collision. Car B wasn't going anywhere. After the collision, it's said that car A has taken off at 40 degrees north of east with a velocity of 9.119 meters per second. So here it was going at 12 meters per second. It was the moving car, now going 9.19 meters per second, but in the upward direction. And now car B goes somewhere. It didn't hit car B head on, or they both would have went this way. It hit a little bit on the high side, ricocheted car A up, and so car B is going to go down. And the question is now, where does car B end up? What is the final velocity of car B, and the angle velocity being a vector has a magnitude and a direction. So what we want to remember from the momentum chapter is that momentum is conserved in a collision. So we're just going to break this up into two pieces. Momentum before the collision equals momentum after the collision in the x direction. Momentum before the collision plus momentum, or equals momentum after the collision in the y direction. So we're going to need to break this final velocity of car A into an x component and a y component. And we can do that because we have one side, we know one angle. It's just back to trig again, where as you remember, the cosine of the angle equals the adjacent over the hypotenuse. The sine of the angle equals the opposite over the hypotenuse. So the adjacent side of this triangle in relation to this angle is the x side, the horizontal side. And so we can say, if we're looking for the adjacent side, we could say that it's cosine of 40 times the hypotenuse, which is 9.19. So here I have cosine of 40 times 9.19. Here I have sine of 40 times the 9.19. And that's the x portion and the y portion of this. So now let's move on to our momentum equation. This is elastic collision, which means after the collision, the items went their separate ways. They did not stick together. Inelastic would be as if they stuck together as one piece and moved as one mass after that. So this one is elastic. And the formula for that then, the general formula, momentum before the collision, and we use a p, this chapter is using a p for momentum, is equal to momentum after, and we know that by definition this momentum is equal to mass times the velocity. So we have mass 1, mass 2 plus, mass 1, velocity 1, mass of car 1 times its velocity, plus mass of car 2 times its velocity before the collision has to be equivalent. The momentums are equal, so mass of car 1 doesn't change, but it has a new velocity, so we're going to call it v prime, v1 prime, and mass of car 2 didn't change, but it has also a new velocity, so we're going to call it v2 prime. And now we're going to do this just for the x direction only. Mass of car 1, 950 kilograms. Its initial velocity of 12 meters per second, plus mass of car 2 is 950, and its initial velocity is 0. So we can just zero out this portion for the x direction. It didn't have any velocity, so its mass times velocity there is 0. And afterwards, we have the same mass of the car, the 950, for car 1, and its new velocity, but its velocity in the x direction only, is this cosine 40 times 9.19. All right, and then we have the mass of car 2, which is 950, times the velocity 2, which is the thing that we don't know. Okay, so we're just going to put it as v2 prime. And then we can solve this equation for this v2 prime, because all these other ones are just numbers, and we can find that and this is for x direction only. Okay, and so what we're solving the equation for is this piece right here, this v. Well, we started out calling them A and B. Now we're calling them 1 and 2. So I guess I'm going to change this 2 to a B to try to be consistent. So VB in the x direction, when we can get this down to an actual number, if you do the math on this, you'll come up with 4.96 meters per second. So here we now have this 4.96, and the next we'll use the same momentum equals momentum before equals momentum after a collision. We use this same one, but we're going to go y direction now only. So I'm going to do that right over here. So I have mass 1, velocity 1, and this is all in the x direction. There's nothing happening in the y direction with car A or car B. This one was completely stopped. This one's going horizontal only, no vertical component of it. So this whole half of the equation for the y direction is 0. All right. So for the y direction, we have 0 equals, and that's this whole half. And then mass of car 1, which is 950, and the new velocity, which is now, it's this y portion of it. So we have this sine of 40 times 9.19. And then this one, we'll see, this one's going up. We're going to assign the y-axis a positive direction and a negative direction. And car A went up. So what we're basically saying in this equation is, since there was no y component over here, the amount that car A goes north is the same amount that car B has to go south. The same relationship. Okay. So we're going to say, but we're going to call this one in a minus direction. So we can say plus 950 and then minus this VBY. And we can solve this equation for VBY. We've got a 0 equals this minus that. And so we could set these two things equal to each other. In any case, when we solve this equation, we get VB in the y direction, and this is our prime, this is our after the collision of 5.91. And now that we have this, now we can see, looking at the green triangle, how we know one side, we know two sides, and once we know two sides, we can find the third side. So it's just Pythagorean's theorem to find the final velocity of B. This was the x component, this is the y component, and this is the total final velocity. So this vector B, the magnitude of it is going to be the square root of 4.96 squared plus 5.91 squared, and that's Pythagorean's theorem. And this comes out to be 7.72 meters per second. And now we want to just, the only thing we don't know is the final angle. And that's our third of our trig formulas, and that is, we can say the tangent of the angle is equal to the opposite over the adjacent side. And in reference to this angle, the opposite side is the 5.91. And so if we want to solve for the angle, we'll say the inverse tangent of opposite, which is 5.91, over the adjacent, which is 4.96. And we get an angle here of 50 degrees. Now, it can be noted that since these two masses are equal, I could have not used the masses at all in this equation because I'm multiplying each velocity times the same mass. It just happens that A and B are of the same mass, and that might happen in, like, if you're talking about pool balls. If you're talking about cars, they're generally not the same mass. I went ahead and worked this problem out that would work for any problem, whether they're equal masses or not. So it's true that for this problem we could have ignored the masses altogether, but that's not true of any problem because if the masses are different, they're definitely important to the equation. Thanks.